stereochemistry of the products that are formed. So I've got the molecule here, and I've got the front-on representation of the molecule. What we need to consider is what the molecule's like on its side first. So if I consider turning it onto its side like this, so I have to lay it, I can hold it there maybe. So we've got our carbon and our oxygen in the plane. Coming towards us is R2, and going away from us is R1. So this is using those perspective lines, perspective bonds to show the 3D structure on the piece of paper. So this is our molecule here. Now, our nucleophile, so let's say it's the H-, it applies the same for the cyanide as well. This H-, it can't attack this carbon from any particular direction. It has to come across one of two very specific approaches. So we can either come in roughly in along this line of attack, or from the equivalent coming from below. So on the molecular model, that's coming in from above here or from underneath there. It can't come in from over here, it can't come in from sort of here, it has to come in from one of these two approaches. Now why that is something that is that's something well above A level. It is something where you have to consider the molecular orbital theory of bonding, which is a university topic, so we're not going to delve into that, but you do need to know that it can only approach upon these two pathways, and that impacts the products that are formed. So I have two of the models here, so we see these are both identical to start with, and we'll see what's formed when we attack a hydrogen from above or below the plane of this carbonyl bond. And that language I'm using, that's matching the language you're going to need to use in your exam papers. So if we take this one here, so I have here represents a hydrogen. Now if this attacks from this time above, it's going to break one of the carbon-oxygen bonds, so I'll just pull apart one of those, and it forms a bond with the hydrogen. Now we can have, this can represent one of the lone pairs of electrons, almost like the negative charge on the oxygen. So this is the molecule that's formed in that case. Now if we attack from below with a different hydride, so if it comes in from below, I'm going to break so it's then going to attach in that position instead. Let's reattach that. And so we've formed our two molecules. Now, they've got all of the same bonds. They've got one bond to one of the hydrogen, they've got a bond to the orange, bond to the purple, and a bond to our oxygen. So they've got all the bonds, but if you look at how they relate to each other, you should notice that these are enantiomers of each other. These are optical isomers of each other. They're not exactly the same. So we form two optical isomers. So we form, I'll draw them out. Sorry, that should be a single bond. And when we form the mirror image of that, so we form two optical isomers. Now each of these can then react with some hydrochloric acid. And we'll put the hydrogen onto it. We form two alcohols. Well, it's the same alcohol, but it's the optical isomers. It's the two enantiomers of that alcohol. Now the requirements for this to happen is that we need two different groups here. So in the example I showed you earlier, this molecule here, so the methanol, these are both the same. So these aren't going to produce, this isn't going to produce an optical, a stereo stereo. It isn't going to produce stereoisomers. It's going to form just one product. The propanone do the same thing. So it's not going to form optical isomers. It's just going to form one single product. But if we took ethanol, now if it depends on what we use. So if we use cyanide, it will form optical isomers because we'll have 4 different things attached to the carbon. We'll have hydrogen, oxygen, CH3, and CN. If we use the hydride, then we'll have 2 hydrogens, so it won't be optical. It won't form optical isomers, but for the cyanide, it will. So, what they'll often ask you to do is maybe to draw the 2 enantiomers. So draw the 2 products and how they relate to each other. Would be maybe some of the wording of the question. So what they're looking for you to do is draw the 2 structures and make it clear that they're mirror images of each other. They might want you to identify the type of mixture that is formed. So it will form a racemic mixture. So it's not going to form one of these isomers. It's going to form both of them, and it's going to form them in a 50-50 ratio, which is our racemic mixture, an equal ratio of each enantiomer. So we form a racemic mixture. Now, to justify this, why it forms a racemic mixture, you need to say the nucleophile is equally likely to attack from above or below the plane of the CO. So the points they're looking for is the